Sherwood's awesome.
They won state last year.
Yeah. Couple things here. Remember yesterday we talked about similarity in triangles, and the relationship that we used yesterday to show that two triangles are similar was the angle-angle relationship, right? We know that if two angles of one triangle are congruent to two angles of another triangle, then guaranteed those two triangles are similar. We're going to look at a couple other ones today. All right, so so one of them is side, side, side. Now this is a little different. Remember, we had than the side, side, side we're already familiar with. If we go back earlier in the year when we were talking about triangle congruence, we said that if the three sides of one triangle were congruent to the three sides of another triangle, then the triangles were congruent. This is different. This is a similarity relationship, not congruence. What we're saying here is if the ratios of the lengths of the three sides are all proportional, they're all in the same proportion, then you know the triangles are similar. So in this case, we've got the big triangle ABC and the small triangle PQR. And what they're saying is if the ratio of the corresponding sides are all equal. So would everybody agree that side AB goes with side PQ in these scale version triangles? So if the ratio of AB divided by PQ is equal to AC over PR, right? Because those sides go with each other, and it's also equal to the length of BC divided by the length of QR, then in that case we know the triangles are similar, okay? Because the corresponding parts all have the same scale factor, right? They're all in the same proportion, okay? All right, so the other one we get is side angle side. Same kind of deal. If we know that an angle of one triangle is congruent to the corresponding angle of another triangle, and the lengths of the adjacent sides of that angle are proportional, then it works, right? So in this case, if we know, for example, that angle X is congruent to angle M, and then the sides that make up that angle, right, that enclose that angle, are proportional. So XZ over MP, or rated ZX over PM, same thing, equals XY over MN. You got it. Okay? Then you also know that they're similar triangles.
Wait, so just by the angle?
So, right, by the two sides being proportional and the included angle being congruent, then you know that the triangles are similar. Okay. If you're given enough information, if you're told that. Okay. So now let's practice these a little bit. Let's try a couple examples. Oh, let me go back. Let me go back. Okay, this PowerPoint will be, it's already actually, I think. It's not, I'll make sure it is on the website. Okay. Okay, so what about this then? Let's use the side similarity here. Which of the three triangles are similar? Well, we don't know. I mean, they might look similar, but it doesn't matter what they look like. How would we find out? We'll have to just test.
Wait, what do you mean test? You can't understand.
That's a 10, yeah.
It's 3. Yeah, it's 6, 9. I know, but it's just I can't. The yellow I can't read.
And the yellow's hard to read. Here, let me write the yellow ones. Those are hard to see. Let's see. How about this? So that's a 10, 6, 9. Yeah, go ahead. Okay, so now what are we going to do with this? How are we going to test to see which triangles are similar? Gabe, what do you think?
To see if all the sides are even, then we'll go.
What do you mean by even?
Like 2, 4, 6, 8.
Okay, well, there's more to it than that. You're on the right track. Does somebody else want to add something to that? Yeah, Taylor.
No, but I think the first two triangles. Yeah, no, these two over here.
Okay, why do you think that?
Because I did it.
Well, what'd you do? That's what I'm trying to get.
I just did 9 and it was 9 to 12.
Okay, so the ratios are all the same. The ratios of corresponding sides are all the same. right? So we could test, right? We got to see which are the corresponding sides. Now conveniently they have this color coded for us. The red sides all would go together, right? Because the red sides are the short sides. The kind of, I don't know, lime green sides are the medium sides, and the long sides are the blue sides. And if these are similar, wouldn't you agree that the short goes with short, medium goes with medium, long goes with long? It has to, right? So we'll look at those ratios. Let's look at the ratios of the red sides. Let's compare the first two. So we get, if we do big to small triangles, we get 6/4 is the ratio of the red sides. What about the blue sides? The blue sides we're going to get 12/8, right? So 6/4 reduces to 3/2. 12/8 reduces to 3/2. What about the yellow sides? 9/6 also reduces to 3/2. So we know then that the first two are similar because the corresponding sides are all in the same ratio. The same scale factor tells us, the relative sizes of those. What is the scale factor? If I asked you for the number that's the scale factor, what is it? What's the number that tells us how much bigger this triangle is than this one? 3/2. Yeah, right? It's just the ratio between corresponding parts. It's simplified, right, down to a simple fraction. So 3/2, or even 1.5 would work. Okay. Now, what about this other one? Does it work? Well, we can see if we check here, 6/4. Well, that's in the ratio 3/2, but the others aren't, right? If I try 14/8, that's not in the same ratio.
So they're all each side, whatever. They're all 3/2.
They would all have to be, right? Here's the red ratio for the first two. Here's the blue ratio for the first two. And here's the yellow ratio for the first two. Now, if we look at the second two, the red ratio is 6/4, but the blue ratio is, 14/8. Now, those are not equal, right? So they're not similar. Yep. Yeah, so you can see right away this can't work because if the short sides of both of these are the same, right, and the other sides are different, well, obviously those triangles aren't the same shape, are they? They couldn't be. Yep.
Instead of going like 6/4 or something on the first two.
Mm-hmm. Okay.
I went 9 and 12 like the green side and the blue side, and then I did the green side and the blue side.
Okay, and that actually, what Taylor's saying is she did this. She looked at the ratios of this side to this side, the medium side to the long side on this triangle, and then compared the medium to the long on this triangle and found that they were all in the same ratio. Now, it turns out that actually does work. It works because if we set up these ratio equations, we can exchange diagonally and do some tricks. But that's not the way you want to think about it. The way you want to think about it, what's the easiest way to consider this is to always compare corresponding parts between triangles. And the reason I say that is because we don't just compare sides. We also compare things like perimeters. Or yesterday we looked at the height of the triangles, right? Anything you can measure with a measuring tape, once we know what the scale factor is, in this case it's 3/2 or 1.5, any linear measurement should be in that same ratio. So you always want to be in the habit of comparing between triangles, not within a triangle, if that makes sense. We want to find out what the scale factor is and then see if it applies to the other parts of the triangle. Okay? It would work for the perimeters for sure, wouldn't it? We know it would. These are similar triangles, so if we added up this perimeter, we would just get 15 and 12 is 27, and here I'm going to get 18, and if we take 27/18 for sure, that's 3/2, isn't it? It is. I can just divide 9 out of the top and the bottom. Okay, if I measured the heights of these, which we're not going to do, but if I measured the height of that triangle and the height of that triangle, those would also be in the ratio 3/2. They'd have to be. because we could measure them with a line. And if I drew them carefully, those were right angles. Okay? Questions? Okay? Let's try another one. Okay, let's say, now this time, oh, okay, that's from the last one, isn't it? Whoops. Yeah, there we go. Example 2, using side angle side similarity theorem. So this is a little different, right? Now this time we're going to compare two triangles, but we don't know enough information to use side, side, side. Okay, now let me copy this picture down. And I want to be able to draw a little better. So let me copy this picture and put it on a bigger sheet up here. Okay, so there's our picture. Now, given that SP is 4, so they're giving us some stuff here. SP is 4, PR is 12, so that's just this length right here, right? SQ is 5, and QT is 15. We want to try to prove that triangles RST, so that's the big triangle on the outside, is similar to triangle PSQ, that little triangle that's sitting on top of it. Okay, can anybody think of a trick that might make it easier to do this problem? Okay, that could work. Definitely could work, maybe, but there's a little different way we want to approach this.
Also, the 12 and 15 shirts and stack.
Oh, okay, there we go. Now, one thing that's confusing about this, I think, and remember I gave you a little hint yesterday. When you have problems like this where the little triangle is superimposed on top of the big triangle.
Wait, so it'd be SR over ST.
There you go, exactly. But that's hard to see. Does everybody see what we're getting at? This is the length of the big triangle. This is the length of the small triangle. You don't have to do this, but I think it's convenient, at least if you're having trouble seeing this, to take the little triangle and the big triangle and separate them. Just draw them on a piece of paper. So what we've got here then is SRT is the big triangle. So here it is. Or RST, I guess they called it. And the little triangle is PSQ. Right? It just looks like this. Okay, pull them apart. Now, what are some things we know? Are there any congruences there? And do they share any of the same parts? Angle, yeah, angle S, right? Angle S obviously is congruent to itself. They have the same angle. So there's one thing that we can see right away, is that those angles are congruent, right? Now, what about the side lengths? Well, the side lengths are pretty obvious for the little triangle. We're given that this side is 4 and that side is 5. But what's the side length of the big triangle?
15.
Good. Okay, now I heard 20 because we have to add both of those, don't we? So that whole thing is actually, if I go clear from there down to there, I have to add those two segments, right? And then this side length is actually 16, isn't it? Right? Okay, so...
I think you just do the pi here.
Yeah. Well, hold it. Now, it's a great idea, but I should have said yeah, because we don't know that we can't. How come, when could we use the Pythagorean theorem, and why can't we necessarily in this case? It's a good idea. We don't know if it's right triangle. We're not told anywhere, right, that we don't see any right angles up here, so we don't know. Now, it might turn out that it is, but we can't assume that.
So you have to use proportions in the angles.
So we got to use proportions, right? We're going to use side angle side. Now, we know those angles are congruent. Yeah, we'll check the side lengths. We'll check these two sides go together, so let's make those the red sides, how about? So the ratio of big to small red sides would be 16/4. Now the question is, does that equal the ratios of, let's make them the green sides. Big to small would be 20/5. Are those equal?
Yes.
Yeah, they are. In fact, what do they both reduce to? 4. Okay, they both equal 4. So what's the scale factor? 4. Right? Scale factor is 4. The big triangle is 4 times bigger than the small triangle. The sides are that much longer, right? Okay, everybody agree? All right, so we just showed it by side angle side. The two sides proportional, included angle congruent. They're similar. Very good. All right. Okay, did that. Okay, fine. I'm going to skip this one for now. Yeah, I think we're fine. Okay, I think we're good to go. Let me see if I can find. Actually, I know 205's open. Let's go down to 205. That was a good job today. You guys, you redeemed yourself. You were awesome.
Now we don't have to take the mic off.
Well, that wasn't. It's not really based on. Yeah. I'll talk to you down there. I gotta get down there real quick. So hold that thought for just a second.